Hello everyone, I'm Madhyasha Mohanty, a PhD student in the Department of Aeronautics and Astronautics at Stanford University. I will be presenting precise relative positioning via tight coupling of GPS carrier phase and UWB measurements. Precise relative positioning finds numerous applications in the automotive industry, such as in lane-keeping maneuvers, collision avoidance, and safe distance maintenance on entry and exit ramps. The goal of our work is to provide precise relative positioning for a two-car setup using local computations. Among available sensor choices, GPS carrier phase positioning provides high accuracy if the ambiguities are correctly fixed. Traditionally, carrier phase positioning method involves GPS RTK, where cars receive corrections from base stations. However, GPS RTK faces the following challenges. First, base stations are not accessible in all regions. And secondly, degraded satellite visibility in urban environments can cause traditional methods such as lambda to fail while fixing integer ambiguities. In our proposed approach, we use UWB as a complementary sensor. UWB provides high-frequency interranging measurements, is relatively passive and inexpensive, and eliminates the need for a base station. Imagine we have 3 satellites from which we receive pseudorange and carrier phase measurements. The wavefront of these satellites create an intersecting integer ambiguity grid depicted in the lines as shown here. Initially, we start with a large integer search space. Using the code phase solution, we can constrain this into a smaller circular region around the leader car as shown here. In our work, we use interranging measurements from UWBs to create an a priori estimate of relative position. Specifically, we first create length constraints that reduces the circular search space into annular search space. Next, we utilize angle constraints from multiple UWBs to constrain the search space even more into a smaller conical region. Finally, we can then estimate the integer ambiguities in this smaller search space and solve for the relative position vector. Note that we also adaptively constrain the search space using noise and interranging measurements from multiple UWBs. Finally, we estimate the integer ambiguities in a computationally tractable manner by developing a barrier formulation. After optimizing for the float ambiguities, we round them to estimate the integers and thereafter solve for the relative position. We demonstrate our algorithm on real-world data that was collected at Stanford campus. As leader car, we use an experimental lab-built vehicle that is equipped with a UWB sensor, a commercial GPS receiver, and an OXDS that serves as the source of ground truth. We use a commercial vehicle as the follower car that is also equipped with a commercial GPS receiver, 2 UWBs, and an OXDS. The cars were driven on straight paths around campus, maintaining an average separation of about 30 meters. We demonstrate our results on this real-world data. We are able to achieve high accuracy without reference stations, even with degraded GPS visibility and noisy UWB interranging measurements. Note that our algorithm performs the other baselines in providing precise relative positioning. Moreover, our proposed adaptive bounds on the search space perform better at integer fixing than fixed bounds and thus result in an overall lower relative positioning error. We would like to acknowledge Toyota Research Institute TRI for providing funds to support this work, rest of the NAV lab for their insightful discussions and helping with data collection, and finally Stanford Dynamic Design Lab or DDL for providing the necessary equipment and assisting with data collection as well. Thank you.